All right, everybody, thank you so much for coming out for this edition of Climate Science on Tap. The title of tonight, Going to Extremes, the Future of Weather in the Pacific Northwest. So about a month ago, maybe a little bit over a month ago, when Mary and I were talking about what we should be doing the next Climate Science on Tap about, we were looking at current events. And of course, about 2 months ago, we were all thinking about hurricanes. We're still thinking about hurricanes, but of course, in the last couple of weeks, we've been thinking about wildfires. In fact, I don't know about those of you in the audience, but I found out that my cousin's family had to be evacuated. And I'm sure there's folks in this room that know people that have been directly affected. And so, you know, I think that thinking about these impacts and thinking about extreme weather and how it might affect us here in the Pacific Northwest is an important thing to do, and it's pretty timely. So I welcome you all here to this event. I want to also just give a shout out to Naked City for hosting again. So thank you, Naked City. Yeah. So be sure to thank your server as well, and have a few beers. So, you know, how is climate change impacting weather in our region? Will floods and droughts be the new normal? And how will people and wildlife cope? That's the way we describe this, and that's one of the things. Those are the things that our speakers today are going to be speaking about. We're really going to be focusing in on the relationship between extreme weather events and our changing climate. So it's my pleasure to introduce our speakers. I'll go ahead and introduce all three of them now, and then I'll turn it over to our first speaker in a minute. So our speakers, Rachel White. She has a PhD in atmospheric physics from Imperial College in London. She now works on atmospheric dynamics research, looking at how large-scale waves are created and how they travel through the atmosphere, affecting our weather and our climate. Rachel moved to Seattle from the UK nearly 3 years ago. You'll be able to tell from her accent. And fell in love with the mountains, the city, and the people here. When she isn't researching climate or out in the mountains, she's actually working on learning aerial circus. Yeah, aerial circus. Her latest personal project is trying to combine her climate expertise with her aerial circus skills to create climate science on air. That's a real thing. And so keep an eye out in the sky, perhaps, for her first video, which will be coming up later this year. So, Rachel, let's give it up for Rachel. Our second speaker tonight will be James Rufo Hill. He holds a Bachelor of Science in Meteorology and worked in the private sector weather forecasting before moving to Seattle 11 years ago to study climate change adaptation. He earned a Master's of Urban Planning at UW and has been working on climate resilience at Seattle Public Utilities for the past 10 years. His environmental ethic was formed while serving in the Peace Corps in the Dominican Republic. And I actually learned that was also his honeymoon. So he was really dedicated. He went through 4 hurricanes, so you have relevant experience to tonight's talk. James is the father of 3 daughters, each of whom receive a personal weather briefing each morning. He is better than Alexa, for sure. So let's give it up for James. And our final speaker tonight is Josh Lawler. Josh received his AB from Bowdoin College and his MS and PhD in ecology from Utah State University. He's now the Denman Professor of Sustainable Resources Sciences in the UW School of Environmental and Forest Sciences, and he co-directs the Center for Creative Conservation. They do some pretty neat projects. He has served as a lead author for the last U.S. National Climate Assessment and as a contributing author to the Intergovernmental Panel on Climate Change, the IPCC 5th Assessment Report. Josh is interested in how climate change can drive shifts in plant and animal distributions and the implications those shifts have for both natural systems and humans. And of course, that seems all very good, but sort of dry. And so I asked him for something personally interesting about himself, which he had to Google on the internet. But what he came up with was that he is the father of 2 sons who are climate advocates at age 7 and 11. So he's starting him off right. All right. So let's give it up for Josh. So with that, I'd like to go ahead and turn it over to our first presenter, Rachel White. She'll get us started off tonight. Thank you very much, Rachel.
Okay, so thanks, John. Thanks, everybody, for coming out here. I'm going to start off by talking a little bit about what extremes are. And so we need to define an extreme event. We're talking about extremes, we're talking about sort of hurricanes, but how do we define one? And essentially, by definition, it's something that doesn't happen very often. So it changes depending on where you are. So here I have a picture of sort of snow in Alaska, and that might be a pretty normal day in Alaska during winter. But given that we think like a small dusting of snow is a lot of snow in Seattle, if we had this much snow in Seattle, that would be an extreme. But it's not an extreme in Alaska. And we have similar things. We can look at monsoon rains in some regions. They have a lot of rain. But again, when we have that much rain in Seattle, it causes extensive flooding because we're not used to that level of precipitation. We're not used to that level of rain. And so when we're trying to study extremes, the issue is that we don't actually have many examples to look at because by definition, they're not happening very often. And so when we're looking at, well, how is climate change going to affect extremes, we have to sort of take a step back and look at, well, what's causing the extremes? And how do we expect that to change with climate change? So this is just a picture looking at what our future looks like. And so we're looking at a map of the US, and we're looking at the temperature change that we're expecting to see by the middle of this century. So in about 30 to 40 years, what's the temperature change we're expecting to see over the US? And so if we look over here in Washington and look at this scale, it's about 2 to 3 Fahrenheit warmer than it is now, or than it was sort of 20 years ago. So that gives us an idea of what we're expecting to see in the future, that we're expecting temperatures sort of about 3 Fahrenheit warmer than they have been. And if we look towards the end of the century, so this is looking further into the future, 80 years into the future, we can see the picture is slowly getting hotter and hotter. And so, again, we can apply that to extremes and say, well, what do we expect this change in temperature to do to extreme weather? What do we expect this change in temperature to do to extreme weather? So I'm going to cover sort of a few different extremes. And the first obvious one we can do is heat extremes. So when we talk about climate change, it's also called sort of global warming. And the idea is it's really based on the fact that the Earth is warming up. And as part of that, the climate is changing. Circulations are changing. The amount of rain is changing. But all of it is based on the fact that the world is warming up. And so as the world warms up, here we have sort of two distributions. So our black one is telling us the probability of a temperature now. So here's our average temperature. That's the one that's most common. So on any particular day, it's most likely to be this temperature. And then as we go out towards really hot temperatures and really cold temperatures, the likelihood of those gets smaller. And so you can see it drops off towards either side. And so here we have hot extremes. So those days that don't happen very often, but are really very hot. And then on the other side, we have these cold extremes, the ones that don't happen often, but are really cold. And what happens with climate change is we shift this entire black curve to this orange curve here. And so we're shifting everything towards warmer temperatures. So we're making all of our temperatures, all of our days are going to be hotter. We're still going to have some cold days. We're still going to have some hot days. But we can look at what happens to these sort of ends of the distribution. We call them the tails of the distribution. And so as we shift this towards warmer temperatures, we do see that we get less extremely cold weather because those really cold days are now slightly warmer. So there are fewer of them that are really, really cold. But we also get more extremely hot weather. So because we've pushed all of our temperatures towards warmer temperatures, we now have a higher likelihood of hitting these really hot temperatures over here. So things like heat waves, if we define a heat wave as what we think of now as really hot weather, we're expecting to see more of those into the future, just because the whole distribution, the whole global temperature is getting warmer, because all temperatures are getting warmer. We're still going to have this range of temperatures. Some days will be colder than now, other days will be hotter. But we expect to see more of these ones that are really hot. So we can then move on and say, okay, so that's sort of the temperature one. That's the one that's sort of easiest to understand. But what about extreme rain? How can we sort of decide how temperatures getting warmer is going to affect extreme rainfall. And so the sort of examples I have is to think about the fact that hot air actually holds more moisture. So if you've ever thought about why hair dryers or your tumble dryer is warm and it actually produces hot air, it's because that holds more moisture. So it sucks the moisture out of your clothes or out of your hair quicker than if it was going to be cold. And so the same is also true if you've ever spent any time sort of in Florida, in Mexico, down in the tropics where it's warmer. When it rains there, it really rains. There's a lot of rain that comes out of that sky. And it's because the atmosphere there can hold more moisture because it's hotter down there. So we can sort of think of this atmosphere as a sponge. And so this is the atmosphere now. It's sort of, there's a certain amount of moisture that it can hold. And that's the atmosphere in the future. If we warm up this atmosphere, it's like a much bigger sponge. It can just hold a lot more moisture. And so in terms of everyday rainfall, it's hard to say what that really means. But when we're looking at extreme rainfall, the really heaviest rain, essentially we can imagine just squeezing out that sponge. That's when as much moisture as there is in the atmosphere comes out. That's the heaviest rain event we could have. And if anyone sort of thinks about how much water is going to come out of each of these sponges when you squeeze it, it's clear that with an atmosphere that holds more moisture, you can have heavier rain events. You can get more rain coming out of that atmosphere. And so again, that's sort of the difference between rain in the tropics, where you can get really heavy downpours because you could just have that much water held in the atmosphere. And this is something that we're actually already seeing. So this map shows the observed change in very heavy rainfall. So not just looking at average rainfall, but just looking at those events that are really, really heavy. And this is a change since the 1950s. And so you can see everywhere over the US, we're seeing an increase. So all of the blue colors are increases in the number of heavy rain events. And so over here in Washington, it's not too extreme. But everywhere it's going up. And so based on this sort of very simple relationship between temperature and the amount of moisture the air can hold, and then assuming that in these heavy rain events, pretty much all of that moisture comes out, we're expecting to see heavier rain events into the future. And then we sort of move on to the opposite, and we can look at climate change and droughts. And this is often one that sort of confuses people. It's like, well, hang on. You're saying that heavy rain events are going to get more frequent and droughts are going to get more frequent? That sort of seems a little bit not really common sense. And so when we're looking at droughts, essentially we're looking at the amount of rain we get versus the amount of evaporation, so the amount of water that's leaving the surface. And so in any particular location, exactly how rain is going to change in the future is difficult to predict, and there's quite a lot of uncertainty still around that. Evaporation we expect to go up because, again, warmer air holds more moisture, and so the atmosphere can take out more moisture from the land surface. So if the rain doesn't change, then we would expect to see more droughts. But in some places, we might actually expect to see more rain. And so that's where droughts sort of become quite uncertain. There are some regions where we're quite certain about it. But other regions, particularly Seattle, it's sort of hard to say exactly how rain is going to change. But the other way that we can have a drought, particularly in this region, is with snowpack. And so here we've got actually Half Dome in Yosemite, and we've got pictures from 2012 and 2015. And it's at the same time of year. And so you can see the difference from year to year, the difference in variability you get in the amount of snowpack. And so that fits with our Seattle drought that we had a couple of years ago. And so you may remember in the summer, we had a drought and there started to sort of be water shortages and people were talking about, Seattle was having a drought. And this shows a map of the snowpack in, I think, May around that year, compared to how much there normally was in a normal May. And so you can see in some regions, it's 0%. Like there was just no snow left when there was normally snow. There was 31%, 30%, 12%. There just was so little snowpack that there was no snow to melt in the summer, and that's where we get our water from. And so we can look into this and say, well, what caused this? Why did we have such low snowpack that year? And so here we have two graphs. On the left, we have what was sort of the extremeness of the rainfall or the precipitation that year. How different was it from average? And so white shows that essentially it was normal rainfall, it was normal precipitation. The blue is there was more precipitation than normal, and the red and yellow is that there was less precipitation than normal. So if we're thinking about, well, you know, we had a drought, was there actually less precipitation that winter than we normally have? No, because most of this is white. Most of that is saying it was about normal. What was different is the temperature. And so this one is showing the change in temperature from normal. So you can see over that winter, everywhere was about 5 degrees Fahrenheit warmer than the average temperature. So what that meant was that all of this precipitation that was falling in the mountains, instead of being stored up there as snow, it fell as rain. And so it immediately just sort of ran down those mountains, ran into the rivers, and came out in winter. So then when it came to summer, and we wanted this snowpack, we rely on this snowpack to give us the water in the summer, there wasn't any left. It hadn't built up during the winter. And so this is something that we can think of as this is what climate change will look like. As our temperatures change, as our temperatures get warmer in this region, that summer of drought in Seattle, which wasn't caused by a change in rainfall, it was caused by a change in temperature, will become more normal. It will become more frequent. Okay, and so as Sean mentioned, sort of when we first thought about this event, we were thinking about all the hurricanes that were happening. It's pretty clear that we're not likely to get any hurricanes in Seattle anytime too soon, no matter what climate change does. I think we're probably safe for the next 100 years or so. Then again, the UK just got a hurricane barreling towards them, so don't quote me on that. But essentially, we can look at what climate change will do to tropical cyclones. And so I've just got a sort of pictures of some of the devastation that's been caused by the 4 tropical cyclones that barreled into the Caribbean. I'll even get it in an American accent. And the south coast of the US this summer. And so these are things that really cause a lot of destruction, and trying to understand how they are going to change in intensity and frequency into the future is really important and is a matter of sort of life and death for people. So again, we can think about, okay, well, what is it that tropical cyclones need? What is it that sort of fuels them, that creates them? And then we can think about, well, how will they change? How do we expect those to change with a warming climate? So first of all, we need a warm ocean. That's sort of the energy source for all of these tropical cyclones. And that's why they only happen in the tropics. That's why hurricanes only really happen in the tropics, because you need these warm sea surface temperatures. You need a very warm ocean. You also need an initial weather disturbance. So you need something that's going to grow into a hurricane. They don't just sort of suddenly pop up out of nowhere as a full-blown hurricane. They all start as little tropical storms, and most of the ones actually that come across the Atlantic start in the African easterly jet. So this is just a picture, and you can sort of see it in the clouds. You can see these wobbles in the jet. And they form sort of these little storms, they form tropical depressions, and they travel across the Atlantic. And then as they travel across warm sea surface temperatures, they pick up more energy, they pick up more moisture, and they can grow into a hurricane. And the last thing we need is light winds. Essentially, hurricanes can get blown over. And so if you have a change in wind from the surface to high up in the atmosphere, and so it's much faster higher up and slow down below, the whole system will actually just get tilted over, and then it will sort of blow itself out. It can't sustain itself that well. And so you need these light winds, and particularly like what we call wind shear, so the wind is sort of constant throughout the atmosphere, for the hurricane to grow, for the hurricane to continue to be strong. So we can look at, okay, how are these going to change into the future? Warm ocean. Okay, oceans are going to get warmer. That's sort of the whole global warming thing. Temperatures are going to get warmer. So there's definitely going to be more energy for the hurricanes. Initial weather disturbances. Well, that's a very specific thing about this specific jet, and it's really hard for us to know how that's going to change in the future. That's a very localized thing. So that's sort of still an area of uncertainty. And light winds Again, that's something that's sort of quite localized. It depends on where the hurricane is. So again, that's also a little uncertain. So we've definitely got more energy for these hurricanes. And so there's a lot of evidence suggests that hurricanes are going to be stronger into the future because they have more energy. They can pick up more energy from these warmer oceans. But there isn't really any strong evidence that we're going to have any more of them or any less of them. And so that's what people sort of often ask me is like, oh, there are going to be more hurricanes into the future. And there are some modeling studies that suggest that, and there are some modeling studies that suggest actually there might be slightly fewer. And it's because of the details of exactly how these hurricanes are formed and how they grow that makes that difficult to determine. But what we do know is that they're very likely to be stronger because they can just pick up more energy from this ocean. And the other thing that we can think of with hurricanes is that it matters what the sea level is. So storm surges that are coming in from these hurricanes, when the hurricanes essentially just push the ocean onshore, if the sea level is higher to start with, that storm surge is going to be worse. And so as we're raising the sea level because of the warming temperatures, so the sea essentially rises up for two reasons. And the first is just thermal expansion. Hotter things take up more space, they expand. And the ocean, as it warms up, is expanding. And the other thing is that we are melting land ice. And so as we melt more ice because it gets warmer, that's flowing into the ocean, and that's also raising the sea level. And so the last thing I want to sort of talk about is this idea of did climate change cause? Because this comes up very frequently when we have extreme events, Hurricane Harvey, the wildfires in California. Did climate change cause these events? Essentially, people like to say that climate change is like loading the dice. And so all of these events have a certain probability of happening. And what climate change can do to some of these events, like the hurricanes, it can make them more likely to be stronger. With heat waves, it makes heat waves more likely. It makes snow droughts more likely. But it doesn't mean that we can attribute any particular event to climate change. So I'll now pass over, and we'll hear more about how Seattle is going to cope with these changes in extremes that we might see coming. Thank you very much for your attention.
So our next presenter, James Rufo-Hill, is going to take us now from these big picture background issues and really talk to us about what Seattle's doing to prepare for these extreme weather events. So with that, I'm going to turn it over to James.
Thank you. So that was an excellent introduction. Thank you. I'm going to try to bring it a little more local and talk about a few examples of what we are expecting here in Seattle and how we are preparing for them. So I'm with Seattle Public Utilities, and just as a reminder, we provide most of you, if not all of you, with your drinking water, with your drainage and wastewater services, and with recycling. Climate change is likely to impact, certain to impact two of those services, one of which has to do with your water supply. So another reminder, we are not just in charge of the city here at Seattle Public Utilities, but we have 100,000 or so acres up in the Central Cascades where your water comes from. This is Chester Morris Lake in the Cedar River watershed. Fun little fact, we're made of about roughly 60% water. That's 60% of you right there. And we're also responsible for providing urban drainage, Paradise Paved. This was once a functioning forest, and now we are responsible for trying to make it act like one again. Also pictured here is the sound. We're not going to talk about sea level rise, but just know that we are preparing for that as well. So I want to talk about 4 impacts. I want to talk about extreme rainfall, in particular atmospheric rivers, and for better or worse, very well timed. There's one aimed right at us right now. I'll talk about snow drought, provide a few more specific examples about what Rachel spoke about. And I'll briefly get into heat and wildfires, but mostly going to talk about rain. I will mention Hurricane Harvey because a lot of staff at the city are asking about it right now. Can it happen here? And for reasons that Rachel mentioned, absent runaway global warming, we do not expect hurricanes in Seattle, but we can learn from it. And so what was interesting about Harvey is that it stalled. It just kind of sat over Houston or the Gulf Coast for almost a week. And as we learned about in the quiz, provided the Gulf Coast, parts of the Gulf Coast around Houston with up to 50 inches of rain. Now, Seattle typically gets 37.5 inches of rain a year. Even in its wettest years, like this past year, or the past two, we've received 49 in that span. So in 5 days, it got more rain. Parts of Houston received more rain than we've received in our wettest years. So people, they hear this, they see the impacts, and they ask, okay, can that happen here? Should we be preparing for 50 inches of rain in 5 days? The answer is no, but as you also know, we can be impacted and receive flooding. So let me just point out that this was roughly a 1,000-year event. Now, statistics are tricky at that interval. We don't have 1,000 years of records. But we do have an idea of what a 1,000-year event might look like here. And so I just briefly want to introduce you to the arc storm. Back in 2011, the USGS looked at the paleo record, thousands of years of data, primarily looking at California. They found an event in 1861 where an atmospheric river, a multi-day rainfall, just sat in place and flooded the Sacramento Delta for 5 days. It used to be an inland sea anyway before it turned into deltas or was levied up. Anyway, we know that we can receive, that's what a 1,000-year event looks like in California, and it also can happen up here in the Northwest. The thing is, though, the question was, what, if we can't get 50 inches of rain in Seattle, what can we get? So we at Seattle Public Utilities have looked at the statistics. We've got 20 some odd rain gauges that we've been managing for 40 years. We also have weather service gauges that we can look at. So we have a good idea of the statistics. In one day, probably the most amount of rain that we could receive, a 1,000-year, one-day event, would only be 8.5 inches, maybe 9 inches of rain. In a 5-day span, 12 inches. That's here in the city. With elevation, you get more. It's only 20 to 25 inches in that watershed that I showed you. Maybe at the top of the rainforest, it's only 40. Extreme rainfall, globally, has more to do with latitude than it does altitude. So we, as Rachel explained, we cannot get tropical rainfall here, but we can get impacts. And I'll show you a few pictures of what extreme rainfall looks like here. But let's talk about that arc storm event again. That would be the result of an atmospheric river. Now, this is my favorite image to show. This is like the lava lamp. It just hypnotizes. I'm going to hypnotize you right now. This is from December of 2007, and emerging from the vicinity of Hawaii, pointing right at us, is a plume of water vapor. And that was responsible for Seattle's worst rainfall event on record, December 2007. At any given moment, there are a number of these plumes emanating from the tropics. One right now is hitting British Columbia, and it's going to slowly pass through. And then tomorrow morning, we're going to wake up to heavy rain, and then it's going to pass, and then it's going to come back north again on Wednesday night, and then it's going to come back and forth all this week. So again, it's good timing there. This is our extreme event. We receive really intense convergence zone events. Sometimes we have thunderstorms, but really this is where we have flooding events like this one right here. I think Rachel showed a picture of this from another angle before. This was December 2007. That atmospheric river shut down I-5, and it also flooded a few of our neighborhoods. You can tell by the pixels. This was Del Ridge. Again, this is the wettest event we've seen in Seattle history. Note, it kind of looks like Houston a little bit. Now, it was short-lived. It wasn't 5 days. Houston has different land use. It has different topography. But we can see impacts like this, and so we need to get ready not only for, this was only 5 inches in 24 hours, but we have to be ready for 8 and 9, and we are working that into our plans. Along with atmospheric rivers often comes landslides, particularly after we've had 30 or so days of wet rain, 2 weeks to 30 days of wet rain. We are expecting these to increase. SPU is working very closely with SDOT and with parks to figure out how to better prepare for these. And so Seattle was built for the drip, not for the downpour. In this image, I love to share this image. This was from an intense summertime event in the middle of that drought. The watersheds weren't actually getting a lot of rain that summer, but occasionally there were a few downpours. This was near the Burke Island Trail in the U District, near U Village. It's deceiving though, because see that dead end sign? It's right on the ground. It's not that. This was just a few inches of water, but it's illustrative nonetheless. So what are we doing about extreme rainfall? Well, we're building better gray, green, and blue infrastructure. Gray, larger pipes. We're about to build a tunnel beneath Ballard to help convey our stormwater and our stormwater to King County. So we're gonna build that bigger because of climate change, and we're gonna do that where we can with other facilities and assets. This is an example of green infrastructure. In response to a bad flooding event in December of 2006 in Madison Valley, we bought out an entire city block and built a park, a pond. This was filling up during a testing phase. It was designed for a 100-year event. It hasn't filled up yet, which is good, but we are prepared for an extreme event there. And we're building more of these around the city. And blue infrastructure is something that we're kind of learning from Copenhagen and New York City, who are looking into designing streets differently to potentially become temporary canals during downpours. Something that we're going to have to get used to or think about differently, but the idea is instead of building a crown this way, you build it reverse, and we're just going to have to live with it temporarily. We're going to do that where we can. It's not going to be easy. I want to move on to heat. Okay, so this is a plot, the last 65 or so years of average temperatures during the summer here at SeaTac. You know, it's funny, when I put together this presentation, no matter how I sliced it, whatever 3-month period, whatever month during the summer, if it was high temperatures, low temperatures, average temperatures, the trend was almost always the same. We've seen some of our hottest summers most recently. This last summer was the same. You know, we are not well designed, like we're not well designed for rainfall, we're not well designed for heat. We do not have air conditioning in Seattle like we do in other cities. So we encourage people, particularly our vulnerable populations, to get out and get to spray parks. Not everyone can get out to a spray park. Not everyone can get out to a community center. This is where we're having to do the most work, to work with our elderly populations, to work with our vulnerable populations to help them get the services they need, because we just don't have air conditioning and we're just not used to it in this city. At the same time, we've got wildfires. You know, I showed you that picture of the watershed. We are very concerned about a fire in the Cedar River watershed in particular, because that water source isn't filtered. And so if we get a fire, which we're expecting more of, and we're expecting them on the west side in the future, that has the potential to shut down 70% of our water supply, and we'll be totally reliant on the South Fork Tolt River watershed in the future. So we're concerned about that, and along with it comes smoke. And, you know, we're not going to start putting in HVAC systems everywhere, but we will try to make sure that it's in there with new construction, and particularly not so much with the AC, but the V part. Some ventilation does some good work in keeping the air clean, but it's hard because we've got a lot of vulnerable populations to consider. I want to talk about rising snow levels. Rachel got into this. Here's a plot. Rachel showed the same map image, but here's the in red. This is October to October, the water year, snow water equivalent. In red is what is normal. So the last two are in green and brown. And here in 2015, it was just one of the worst years we've ever seen. This is what this Chester Morris Lake looks like at the end of every summer. Actually, right now, this is what it looks like. We don't have big water supplies like California. We only store for 1 year, and we wait for those fall rains to come back, like they're coming back this week, and it'll start to rise up again. And then we wait for that snowpack to be that extra supply that gets us through the summer. So when we don't have that extra supply, we have to do things. So we have to some things we're doing is raising the level of the reservoir. We're holding more water. We're holding it later. Another thing we're doing is we're asking customers to conserve. And you've been great at doing that. You've been great at letting your lawns go brown. These golden lawns are great for us. So we've got some things to do, but this is a big concern for us. I want to end on somewhat of a positive note and show you a plot of 1930 through today. This is demand. In red is population growth. Now, Seattle Public Utilities provides water not just for residents here in Seattle, but through the metropolitan region. In blue is annual consumption. note that there was a period somewhere around 1990 where the two decoupled and demand started to go down while population continued to go up. The truth is, today we are using water at the same rate we were in the 1950s with, what, double the population or so? This is great. This helps us ease into climate change and gives us flexibility to do more in terms of managing our water supply. It's starting to go up again as population is spiking. You know, you can see maybe we've hit the end of that, but we've got some room to work with. It's really great. So keep those lawns golden and keep, you know, installing low flow toilets where you can. We're going to be in good shape. And I'd love to look forward to your questions later, and I'm going to pass it along, but thanks a lot.
Thank you very much, James. Well, as a proud owner of a golden lawn, I'm doing my part. Well, Noah, we've learned a little bit about what the city's doing and what we all can do to adapt to these changes and prepare for droughts or storms. But with many of you are probably wondering, what about the animals? That's what I care about. What about the animals? And so we've got Josh Lawler here as an ecologist to talk about what wildlife is doing, how wildlife responds to these extreme weather events. And he's got some really interesting examples to share with us today. So with that, I'm going to pass it off to Josh.
Thank you, Sean. So as Sean said, I'm going to try to connect some of these extreme events you've been hearing about to the potential impacts on wildlife in particular. And I'm going to do that, as Sean said, with a series of examples. So I'm just going to step through some examples of extreme events that have happened and how biota have responded, or some of the ways biota have responded. All right, so I'm going to start in January of 2009 in Australia, where there was a 2-week-long heat wave where temperatures topped 45 degrees Celsius, which is 113 degrees Fahrenheit. So it was hot for a while. And one of the things that happened was at a roadhouse in Australia, a bar essentially. This is a picture of budgies, little parakeets. And they flocked to the only shade they could find in the landscape, and they packed in trying to keep cool. And unfortunately, a lot of them didn't survive. Interestingly, these are mostly younger birds. They weren't, after autopsies were done, they found that they weren't adult birds. So the adults had gone somewhere else or had somehow managed to survive at least this event. But the budgies weren't the only things that suffered from this heat event. So these are flying foxes. And during that same heat wave, flying foxes were falling out of trees. Interestingly, these are the older adult fruit bats or flying foxes. And what's interesting about these is for both these organisms, it just got too hot for them. For a lot of times when animals die, when it gets hot, when we have a heat wave, it's because they become dehydrated. But in this case, the temperature was just too hot. So these animals are at the edge of their thermal tolerance. They were at the temperature that their body can take, their physiological tolerance. And we have these types of events in the desert Southwest as too, where there are organisms that are kind of at the edge of their range, at the edge of what they can withstand. And during this same event, koalas came down out of trees and were drinking out of swimming pools and otherwise getting cool. So these extreme events, at least in heat waves, it can have really direct effects on animals. I'm going to take you now to the second event, which happened in the summer of 2002. And this was off the coast of Oregon and Washington. And you may remember that this was the first time that dead zones showed up and were documented off of our coast and off the coast of Oregon. What these dead zones were areas with very little dissolved oxygen. Some places no dissolved oxygen, but between 10 and 30% less dissolved oxygen, 10 to 30 times less dissolved oxygen than would normally be found there. And what it resulted in, this is a really blurry picture, but this is a picture ODF and W shot from underwater camera. It's a lot of dead crabs and it's a lot of dead worms. They're at the bottom of the ocean, the bottom of the near shore environment. There were no rockfish like one would normally find. Those rockfish went somewhere else, but it was littered with dead organisms on the bottom of the near shore. And these dead zones have occurred since 2002. They change. Some years they're more extensive, more severe. Some years they're less. But they've occurred fairly regularly since 2002. What happened, it's believed, is that that we normally get upwelling off the coast of Washington and Oregon. Deep, cold water that's rich in nutrients but low in oxygen is pushed up due to currents and due to winds. Pushed up, and we get an area where there's lots of nutrients and low oxygen, and the water mixes, and those nutrients provide food for the food web, the rich food web that we have off our coast and the Oregon coast. Starting in 2002, that anoxic zone, that zone without oxygen, seemed to get larger and to get pushed much further inland, so that it covered the near shore as well. And in 2002, where there were some hypotheses as to why this might be happening, but they weren't quite sure. One hypothesis that maybe it was climate related, had to do with changes in wind patterns, changes in currents, but there was no real good evidence for that. More recently, in the last couple years, a scientific paper came out that showed that in the past, as we came out of the last ice age, and the oceans were warming very rapidly in this region, we had dead zones that were similar. And you may have heard of the warm water blob that's off our coast in the Pacific. Well, it's thought that as we came out of the ice age, there were events like that. There were warm water zones and fast warming, and at the same time, there were these same types of dead zones. So, although we can't say that climate change caused these dead zones, it may be that we're likely to see more of these dead zones in the future as the oceans continue to warm. All right, the next event I'm going to take you to is in Arizona, near a town called Portal, Arizona, where there was a rain event where 30 millimeters of rain fell in less than 2 hours. Now, we've been talking about many, many inches of rain, so 33 millimeters may not sound much, but remember Rachel said extreme events are relative. So in this part of the world, a little bit of rain happening very fast runs off of the hard-packed landscape and ends up in the valleys, and we get flash floods. And in this case, this flash flood was 35 centimeters deep. And it ran through this valley, this landscape, and it ran over everything that lived there, essentially. And it happened that this took place where there was a long-term study of a rodent population. And this rodent population had been studied for 20 or more years by an ecologist down there. And there were 4 main players in this rodent community. 2 are kangaroo rats, and 2 of these are mice. And one of the kangaroo rat species was much more numerous than the mice, and some of the populations were increasing, and some of the populations of these species were decreasing. After the flood, when many of the individuals died, the population trends were reversed. The dominant organism in the community was different, and for a long time thereafter, the system looked very different. It was a very different composition to the community that was there. So the flood seemed to come through, and it seemed to reset this community and make it quite different. So next thing I want to talk about are invasive species. So these are species, you probably know what invasive species are. They come from somewhere else. They tend to take over or be dominant where they are. In Seattle, we're talking about Himalayan blackberry, English ivy, Japanese knotweed. You know these things. There's thought that invasive species may do better in a changing climate than native species for a number of different reasons. And here's some cases where it's believed that's happening. So in the upper left is after Hurricane Katrina. It was found in Mississippi in some places that non-natives plants were coming back faster than the native plants. Very similarly, in the upper right-hand corner, on Mauna Kea in Hawaii, it was found that the non-native grasses returned after a prolonged drought much faster than the native grasses were returning. Down here in the lower left was a palm oasis in the desert in Nevada. And this burned after a combination of things happened. 1, there was a prolonged drought. 2, there was particularly, there was fire weather, one might call it. It was hot and dry and windy. And 3, the area had been invaded by tamarisk, which burns fairly easily. And so put those things together and this palm oasis burned. The far right is a picture from Wales where a reservoir is extremely low after a long drought. And it's found that the composition of species in the remaining pools of aquatic species was different and was changing rapidly after they got isolated in these little puddles and their interactions started to change. So the last thing, I think this is the last example I want to leave you with, brings us a little bit closer back to home. And it has to do with the reduction in snowpack that both Rachel and James mentioned. Our rivers in Washington, they tend to they have a low point during the summer as that snowpack melts and we haven't gotten rain yet. There's some point in the summer where the flow is particularly low. There was a paper that came out not too long ago, a scientific paper, that showed that those low points were creeping earlier and earlier in the year. At the same time, these rivers are getting warmer. The warmest time of the year doesn't happen to be creeping forward into the spring as fast as the low point is. And so what's happening is the streams are getting lower, and that low point is getting closer to when they're getting hottest. And that has potential impacts for fish. And it's related, not directly, but related to an event that happened in September of 2002 that you may remember. There was a massive fish die-off in the Klamath River in California. And it was due to two main things. First of all, it was due to a drought. But because of that drought, the farmers were diverting lots of water to use in the agricultural fields. And there was a massive fish die-off. The official record is 34,000 fish, but some estimates have it up at 70,000 Chinook salmon alone died in that event. And it appears that it was due to a gill rot disease that they developed because the water levels were low and warm. And when water levels are low, there's less oxygen. When they're warm, well, they're warm. So this event was due to the withdrawals, due to the temperature, and due to the prolonged drought. And as we look forward and we look to lower snowpack and we look to changing in the timing of flow and changing in the temperature of the rivers, what we're also going to look to in many places is less water for us. And if we take more water from the rivers and we combine that with the low flows and the temperatures, we may end up with more events like this if we're not careful. All right, so I started with a picture of a fire, and this is a picture of the same fire. This is the Eagle Creek fire in the Columbia Gorge. And I just want to emphasize something that Rachel really pounded home with those dice, that we can't attribute any of those events I showed you directly to climate change. But those events are likely, many of them, likely to become more frequent or more intense or larger as the climate changes. And it depends on the type of event, but we're likely to see more or bigger or more intense events like that in the future. And I'll leave you with that happy thought.
All right, thank you very much, Josh.
So the question had to do with the Columbia River Treaty and how they've been planning for a while for these impacts. But one impact that we haven't talked about that they've been working on is population change. This is something that comes up a lot. We are among the fastest growing cities in the nation right now, and hopefully that'll keep up, or not. But first off, I want to share some research that came out of the University of Washington recently by Allison Saperstein, who's now with King County. And she did some great work looking at the reasons why people move around. And it turns out that social reasons are bigger drivers than environmental. People move to where they have existing families and networks and churches and jobs, and not so much because there's water, at least yet. And I guess some of the thinking might be that, okay, well, if people who move to California from Oklahoma skip California and move, or if Californians then move to Washington, and then the next generation just skips California to come here, we'll see that boom. So we're thinking about it, and as a city, we are planning for density and we are planning for population change. And as I showed you with water demand, it's in our favor so far that we've been able to offset the population growth, but we're going to have to work on it. In the larger picture, it's a very, very real issue and something that we'll have to continue to think about. But at the time being, we don't expect people to move here right away.
Great, thank you.
The question had to do with, are we looking at bottled water use? Are we calculating bottled water use and how that's changed in the demand? And to my knowledge, we're not, but I bet we have some pretty good figures on how much of our waste includes bottled water. I'm going to work tomorrow and asking my economists. I want to know. I suspect that there's some of that. From what I do know, it has a lot to do with efficient appliances, toilets, shower heads. That was a big deal, particularly commercially, and behaviorally. Like I joke about the golden lawns or whatever, but it's real, and it works to our advantage. So we've got that ethic of conservation here, but I really want to find out now. So maybe I'll share it with the Climate on Tap. Yes, thanks.
All right, great question. There's another one? Yes, sir, you had your hand up first.
We're coming back to your same graph for every question. There was a very large drop in 1 year, and I wondered if that was attributable to a conservation program or if it was a random drop.
I suspect random drop. The question had to do with the famous plot that I ended
It's a
with,
very famous plot.
demand versus population, and I think, to my knowledge, no one's been able to pinpoint specific policies or actions or behaviors, and I think it probably has more to do with the weather actually than anything else. It probably was a cold year or something like that.
Yes,
So,
me
so
too.
the question was whether the dams on the Columbia could be altering the temperature of the water coming out of the Columbia and then affecting the dead zones. I'm guessing it might be possible, but I don't know. I don't know. Do either of you know the answer to that question?
Well, there were studies in the Mississippi River, back when I studied meteorology, that's back in the 90s, there were studies on the Mississippi River Delta and dead zones in the Gulf. They seemed they could be caused, one, by the nitrates and stuff coming down the river, and also by the temperature variation, because now all that warm runoff in the Mississippi, rather than being absorbed into the surrounding area, would be levied straight in the Gulf and causing a capping effect down like an atmospheric cap,
Yeah.
essentially created dead zones based on underwhelming chemicals.
Yeah, no, that's interesting. I don't know if that's been implicated or even suggested, but that's great. Thank you.
Yes, sir.
It's true. So one of my main tasks at the city is to work on planning for sea level rise, and so I helped come up with the maps that show which neighborhoods are going to be underwater and when. And no, Ballard will not be underwater. Golden Gardens is going to be eroded, and parts of Shoal are going to see increasing flooding over the course of the next century. The locks are at 18 feet, which is 6 or so feet above current highest water level. So there's a little bit of room to work with there. Eventually, the locks will have to be rebuilt. With respect to the most exposed neighborhoods, it has to do with Georgetown and South Park are most exposed. A lot of Beach Drive Southwest and West Seattle. Inner Bay a little bit. West Point. We're fortunate here in Seattle to not be as exposed as compared to other cities around the country and world. That said, it's a big problem for those who do live in those aforementioned neighborhoods.
Oh, so the question was, how will the tunnel be affected? Our brand new tunnel.
What about the tunnel? The tunnel, which will be opening soon, is in 5 days.
Sorry.
Is going to be okay with respect to sea level rise. And if it's not, we could maybe build a wall around the entrance, and we could take a bridge to get into the tunnel. The tunnel, it's a separate issue.
Yeah, so the question was about salmon and what the particular problems for salmon might be. So there are a number, and they generally have to do, and I'll talk about the ones that have to do with the inland, and I know less about the problems that might be related to ocean circulation. But for the portions of the salmon life cycle that occur, I wouldn't say on land, but in freshwater, There are a number of problems. One is that the stream temperatures are rising. So there are projections that show loss of what we would call thermal habitat for salmon. So there are salmon, trout, they're what we call cold water fish. They like cold waters, unlike sunfish and bass. Yeah, steelhead like cold water. So, a bull trout, perhaps the coldest of water fish we have around. The projections of loss of thermal habitat for bull trout are extreme, and for some of the species of salmon and steelhead are also extensive. So we expect to lose a lot of the river miles will no longer be suitable because they'll be too warm in 50 to 100 years. So that's one problem. Another is this changing in the timing of flow that I mentioned. And when there are, I mentioned low flows, which are important, but also high flows are important. If the salmon are laying eggs and fertilizing eggs, and high flows come through, it can actually blow out a whole year's worth of reproduction in some cases. So it's the timing of flow that matters, when it's low, when it's high, also the temperature of the rivers. And so there are many ways that salmon will not benefit from climate change.
And I just want to add to that, we at Seattle Public Utilities are obligated to protect the salmon in the Cedar River through a treaty with the Muckleshoot Indian Tribe and through our conservation plan. And we're concerned with flooding scour events where the salmon redds are ruined, and we're concerned with temperature, we're concerned with low flows. So we're in addition to providing you with your drinking water, we're trying to provide the salmon with water at the same time. And just this morning I was in a meeting and I learned that we have counted 530 Chinook reds as of this season, which is like double last year, which is very good news. Although a large percentage of that is suspected to be hatchery fish, but still it's good news. Just wanted to share that with you. It's a lot more than we expected.
A little bit of optimism, that's good. Yeah, back there.
One question about extreme. I'm curious, I was looking for a chart that tracked extreme events. And you say is Ophelia an extreme? It's the first hurricane that is formed that far north in the Atlantic. And is it going to be categorized, and I know this is crystal ball-ish, does it fit your model of an extreme event? And that's the question. The sidelight is we did have a hurricane here in October of '63. The Columbus Day windstorm blew up this coast, and the only reason we don't call it a hurricane is there wasn't a CNN guy standing outside yelling into his microphone. But I'm curious, is Ophelia going to be looked at as an extreme?
Okay, so the question is about hurricanes hitting unusual places, I guess. And so Hurricane Ophelia, which came up off the Azores and recently blew over the UK. And I'd say yes, for the United Kingdom, that is an extreme. That's extreme wind, that's extreme rain, and so it's unusual conditions for them. And so it's extreme in terms of it was an unusual place for it to form. And so we do get these events. There's a lot of variability in what our climate does. There are people I was just talking to Sam before this event started about the sea surface temperatures where that hurricane formed. They were a little bit higher than usual. And so maybe that helped contribute towards this event. Moving. Yeah.
We might just want to put that one down.
And so maybe the warmer sea surface temperatures that we saw around that region contributed to this event being in an unusual place. So these are things that we consider to be extremes. So it's something that is extreme for that particular region. And so any sort of hurricanes, so we do get sort of remnants of hurricanes. They often aren't hurricane strength. And so there's sort of a particular definition of how the wind gusts and how strong they are that defines sort of hurricane versus a tropical depression versus a tropical storm. And then they turn into sort of extratropical depressions as they move further north. But certainly extremes moving into regions where they aren't normally seen would be something else that we'd be looking at, and definitely counts as an extreme for that region because it's not something they see normally in their weather.
Yeah. Can you repeat that as well?
Interesting question. So the question is, how often does an extreme have to repeat to be considered the new norm? At what point is it normal? And so we heard a little bit from both James and Josh talking about sort of a 1 in 1,000 year event or a 1 in 100 year event. And so these are the things this is a way scientists sort of think about extreme events in terms of what is the probability? How often do we expect this to occur? And so it really depends on what you care about. When we're talking about building infrastructure and things like that, you really do want to be looking at sort of the 1 in 100 year event. But you also, a 1 in 20 year event can cause a lot of damage. And so there isn't a one single point that every single person will agree, okay, before that it wasn't an extreme, and after that it is an extreme. But we're usually looking at something that happens sort of once every 20 years, once every 30 years, something like that we would consider to be an extreme event.
Yeah, I'll add that SPU most often defines an extreme rainfall event as a 25-year event, 96th percentile, 4th percentile, at any duration. So that'd be a 1-day 25-year event or a 5-minute 25-year event. And I cited that 8.69 inches is our new 1,000-year event. We're wrapping up a study of our rainfall statistics, and the last one we did was in 2003, and so we had SeaTac's Rainiest Day occurred in 2003, and we had extreme events in 2004 and 2006 in Madison Valley, and 2007, the rainiest event the city's seen. And then we had a bunch of events in 2013, 2014, 2015. People started saying, we need to figure out what's going on here. And it turns out that the day-long events, extreme events, 25-year and greater, have gone up by 20 to 30% since 2003. And that's somewhat consistent with the map that Rachel showed earlier. So we've seen that at the day-long events. And it turns out that the statistics show that the short-duration events, those convergent zone or thunderstorm events, 5-minute, half-an-hour events, aren't getting worse. We really want to get to the bottom of that, so we're going to continue to look at it. But the day-long events are getting more extreme. They have gotten more extreme, and the research shows that they will become more extreme by 20 or so % by the end of the century. Such that we now say that a 100-year event, what we used to call a 100-year event, is now a 25-year event, which is a big deal. And it has major implications for how big we build our infrastructure, and it's problematic for sure.
To summarize, sort of looking at Hurricane Harvey and the warm temperatures over the Gulf Coast, and how computer simulations and perhaps forecasts weren't particularly accurate about what was going to happen. And I guess the question is, like, how are we using this to look to the future?
Yeah, I know, in terms of the priority given to maybe a sea surface temperature anomaly above standard, are they looking at maybe adding more priority to that in the algorithm?
So there's a lot of research going on about hurricanes and really trying to understand much more about how they strengthen, when they strengthen. There's a diurnal cycle to them. And you're right that a lot of computer models don't always get this right. And there's a lot of very detailed physics in there about exactly how it's going to change direction, when it's going to change direction. And knowing exactly what those conditions are is very difficult. And so there's sort of, I guess there's two separate parts of it. There's a lot of scientists working currently now just to try to understand more about what is it that strengthens a hurricane? How can we predict this hurricane better? And what do we need to include in these models to get them to be more accurate? And some of that might be just having more accurate observations of the current conditions, having a denser network of observations, so we know what the conditions are now. We know what the wind conditions are everywhere in the atmosphere now, so we have a better chance of forecasting them forward into the future. And so I guess with that, we're getting into the weather idea and this idea of chaos. And so sort of an area of physics that essentially says that very small errors, very small differences can grow very quickly, very rapidly over time. So if you have a small error, okay, maybe your wind was 1 meter per second faster than your observation said it was, or that your estimate said it was. Over 24 hours, that can cause your hurricane to be going in a different direction. And so these are sort of some of the constraints on the weather forecasts. And so it's sort of this competing side of we also need better observations, but we need to better understand the hurricanes. But on the side of the climate, there's also definitely research going on and looking at, well, how are the warmer surface temperatures affecting this hurricane? But again, we go back to this sort of idea that extremes don't happen very often and we don't have a big pool. We don't have an example of Hurricane Harvey in exactly the same place with cooler sea surface temperatures in that region. And so it's sort of hard to piece apart what was caused by those sea surface temperatures. And there will certainly be people running these, running climate models, running sort of higher resolution weather models with different sea surface temperatures, trying to say, well, what would have happened to Harvey if the sea surface temperature hadn't been warmer, if it had been, say, average sea surface temperatures for that year? And that's where we sort of get into these climate attribution studies, where people start to say, okay, well, it was, there was a certain percentage chance that Harvey was stronger or hit the coast because of those surface temperatures. But because it's so recent, that's science that still needs to be done on Hurricane Harvey, but it's definitely science that is being done.
Just to add perspective on how we are approaching the city. So with respect to weather, we've moved away, as has much of the weather community, away from focusing on one deterministic model favoring, say, what the Euro says today versus the GFS or whatever, and moving toward probabilistic ensemble forecasts. So, for example, just this morning, the Euro said we were going to get, or pardon me, the Tolt River watershed was going to get 11 inches over the next 7 days. The GFS said 5.5. But if we looked at the model spread, you can see there's some disagreement, but we're going to plan for in the middle, be aware that there could be as much as that. So that's, we're looking at much more than favoring just one particular model. The Weather Service has been great at this. And that sort of lesson is being applied to climate change as well. We're on our third generation of climate modeling for our water supply. We've moved from one model to 3 models. To the last iteration had 40 runs that we were comparing, and so we're basing our decisions on a range of uncertainty and scenarios rather than just a narrow set of information.
Cool. All this science is making me thirsty. So don't forget to get your waiter over there, your server, and grab another beer. We want to make sure that the folks here at Naked City know how much we appreciate this space and being able to do this here. Actually, I have a question for you, Josh, because I think a lot about human-wildlife interactions. I remember seeing, I think it was one of the hurricanes most recently, someone had some pictures or some video they had taken. It was a taxi cab driver who said that a peregrine falcon had taken refuge inside his taxi because of the high winds. And I'm wondering, what do we know about human-wildlife interactions in the face of extreme weather events?
No, that's a great question. So I think there's some. I think at this point it's mostly anecdotal evidence, but there's some evidence that there are likely to be more human-wildlife interactions in the face of climate change. One of those that's and none of this is really well-documented science yet. By anecdotal evidence, I mean there are some case studies. Some things have happened, and people are trying to draw conclusions from them. And one are the increase in shark attacks that have occurred off several coasts. And it's thought that the food is being driven inland, or the distribution of food is different, potentially. That's one hypothesis. I think there are other examples of grizzly bear. We might expect more human interactions with polar bears as polar bears become more terrestrial and end up on land instead of ice. So it's likely that as animals are pushed out of where they need to be, or they have to move around in response to extreme events, that they're going to run into people. So I don't know of any studies that have really made clear links between increased interactions, but I think there's lots of little bits of evidence that's not real hard evidence yet.
Look at the event that's just occurred at Sakhalin Island with bears. I mean, that's in the news now. They're having to kill a number of bears because they're having interactions with humans. And the bears are skinny.
Yep.
Because people are taking the fish. Who's the invasive species?
That's a good question.
All right, other questions? Yes, in the back.
The question is for animals that rely on snow, particularly mid-elevation snow, but snow in the Cascades. Is there any research that indicates what may be happening to them or what might happen? And it just so happens that my lab has done some research on some modeling for wolverine. So wolverine's a fairly extreme example of an animal that really needs snow. It needs snowpack for denning and lives at high elevations in colder forests. And so the model, we've run some fairly simple models that look at sort of just the temperature envelope and the sort of the climatic envelope they live in. And then we've run some complicated, complex population models that take into account snowpack and vegetation and where people are and population dynamics through time. And you put all of those modeling efforts together and they show that wolverine populations will not fare well as the snowpack decreases, as you might expect. And pretty much in the Pacific Northwest, all our models indicate that there's only one little pocket up in BC where they tend to potentially do well. But animals that are going to rely on snowpack are going to see a decrease in available habitat. And that's all are higher elevation animals. Animals that require colder environments are likely to be the ones that see some of the most impacts. Yep.
So the question was, the chart shows that there's increase in extreme rainfall over the US, and it actually showed a decrease over Hawaii. And the question was, is there a good reason why there is a decrease in extreme rainfall over Hawaii? And the answer, I'm afraid, is I don't know. I will have to look that one up and get back to you. Thank you, Emily.
Ooh, a stumper from a friend even. Ouch. Do you have another question back there in the back?
So 2015 was the big crowd here and had a major impact, obviously. What's the likelihood of future, or the likelihood and the frequency of similar events?
All right. You can tag team it. It's fine.
So part of that will depend on what we do on our future emissions. And so the graphs that I showed for the temperature that we expect to get depends on a certain emission, what we call emission scenarios. And so there's, at the moment, there's sort of four main ones of what do we as a species, as a society do about climate change? How much do we reduce our carbon dioxide emissions? And so that one was sort of for fairly high emissions. It's the road we seem to be going down at the moment. But if we switch over to more renewable energies and reduce our carbon dioxide emissions, we could significantly change that. But what we saw was that a change of sort of 5 degrees Fahrenheit was all it took to bring around that Seattle drought. And we're already looking at a change of maybe 3 degrees Fahrenheit by the 2050s in this high emission scenario, and sort of 5-6 degrees Fahrenheit by the end of the century. So by the end of the century, in that emission scenario, that's a normal year for Seattle. Hopefully we do more about that, and so we go down a different emissions path, and we get a smaller change in temperature. So the Paris Agreement is sort of aiming for a 2 degrees Celsius, so around about 4 degrees Fahrenheit as a total temperature change, and aiming for slightly lower than that. But again, that's sort of close to making that our norm. James?
Yeah, well said. I mean, 2015 is what we are expecting to see under a normal summer by, I don't know, 2070 or so. That's just going to be a normal summer. So think about it this way. 2015 was an extreme year. In 2070, an extreme year is, we don't even want to think about it, but we're preparing for that. That's what our modeling shows us that we have to get ready for. And yeah, it's climate change for sure. It's what we're expecting.
Yes, sir.
Okay, so essentially the question's looking at circulation patterns and how they might change in the future, particularly with this idea of, that we haven't really talked about, this idea of Arctic amplification, where the temperatures in the polar regions are warming much more quickly than temperatures elsewhere, partly because of melting snow. So snow does a very good job at reflecting sunlight. So as soon as you sort of melt that snow and that sea ice, you're absorbing that sunlight at the surface instead of reflecting it. And so you've got more energy coming in and it's going to warm up more. And so the idea is that as you're changing the temperature of the poles more quickly, you're actually changing the difference in temperature between the equator and the pole. So you're changing this temperature gradient. And it's things like temperature gradients that are really dictating the circulation patterns. So there's this idea that the jet stream, in fact, might shift further north with this change in climate, with this change in the temperature gradient. And as the jet stream shifts further north, that's sort of pushing all of these storms that come across the Pacific and come into the west coast. And so it might change the pattern of exactly where they hit. And so the reason we are so much rainier than California is because we get all of these storms and they're all sort of coming into the Oregon, the Washington, the BC region, and they're not going as far south as California. And so this idea is if we start shifting this jet stream further north, we actually might shift these storms further north and they'll stop coming into sort of the lower latitudes and they'll just hit further north. Most of the evidence sort of from the climate models is, whereas we are expecting to see these shifts in the jet stream, they're relatively small. So we're sort of looking at sort of a degree or two of a shift. And so in sort of a big pattern, it's going to really matter for the people who are on the edge. If you're on the edge of that point where you were getting the storms and now you're not, that's going to be really significant. Again, it sort of depends on the emission scenarios, but it sort of looks like, 1 or 2 degrees, so sort of a couple of 100 kilometers by the end of the century is plausible. But I don't think that's sort of going to affect us too much because we're sort of fairly slap bang in the middle of that band of where the storms are going to hit. It would take a pretty significant shift in the circulation for us to get a very different pattern. That's not to say it couldn't happen, but that's not a robust prediction of the climate models right now.
How is City Light preparing? Well, we work very closely with City Light. Both City Light and SPU are largely dependent on the water cycle, so we've been among the first to prepare. They have a great team in place, and they have done a few rounds of modeling. Their impacts are a little different than ours. The energy market, the timing is different. So they have demand concerns in the winter versus the summer that are totally different than ours. They also have some glacier melt that they're dependent on because their source is up in the Skagit in the North Cascades, Mount Baker area. So it's a different hydrological profile, but they're doing great work. And they've been technically carbon neutral since I think 2005. They're showing the rest of the city how to do that. So they're doing great work. That's what I'd say.
Okay, so the question is about permafrost melting affecting the jet stream and affecting the variability of the jet stream. And so the permafrost melting is certainly going to affect the atmosphere through the fact that there's methane trapped in the permafrost. And so as the permafrost melts, it's releasing that methane into the atmosphere. Methane is also a greenhouse gas, and so that's sort of one of these positive feedbacks. So as we warm up the Earth, as we melt this permafrost, there's more methane, so it warms up, so it melts more permafrost, so it releases methane, etc. In terms of anchoring the jet stream, that's not something I've heard any science on. Again, it's going to be something to do with the temperature gradient. So it's not entirely impossible that by melting sort of the snow, again, we sort of go onto this polar amplification idea, that you're changing the temperature gradients, and so you're changing where the jet stream is. There's a lot of research looking into the variability of the jet stream, so this idea of the wobbles or the waves in the jet stream and whether those are going to change in the future. So we've seen quite a lot of those. They can give us warm extremes, but they can also give us cold extremes, particularly on the east coast of the US. A lot of the times they have those very cold air outbreaks. It's because the jet stream sort of wandered up north, and then it's bringing all this very cold Arctic air down onto the east coast. And so that's just because the jet stream sort of got this very strong deviation in it. Whether that's something that's going to increase in climate change is still sort of relatively uncertain. And so, yeah, essentially the science is still out. We're still working on that question for you.
Great. Well, okay, so speaking of questions, I have another question. As those of you know, the sponsor for this event is Cascadia Climate Action, and action is what we're all about. So to each one of you, one thing that the audience can do when it comes to climate change.
replace your shower heads and let your let your yards go. Seriously though, well that is what I would say. I mean, you've been doing a great job conserving. Keep it up, especially when we've had a warm winter, and work with us at the utility when you do see flooding in your neighborhood. Let us know, call us. That data is very useful, and it helps us plan better. But in general, I'm fortunate to work in such a city where people care. So thanks.
Okay, I guess I would go slightly larger scale, and I'd say do the things that you're doing now. Come to events like this. Talk to people. Talk to your friends. Talk to your family. Talk to the people who don't want to do something about climate change, who think this isn't something that we should be doing about, and get the discussion going. Don't try to convince people or change people's minds, but just start a conversation about this. This is something that's going to affect all of us, and so this is something we should be talking about. Amongst all of us. And so it needs to be something that politicians know that we care about, that the people who are making the decisions know that we care about. So that's the one thing I'd say. Start conversations with people. Get this to be something that we talk about, instead of being something that we're scared of or we don't want to talk about because, it's far off, it's in the future, and we're more interested in what happens sort of tomorrow, which is an intrinsic human reaction. But this is something that's going to affect all of us, and so we need to be talking about it.
Excellent. All right, let's see. And I'll add leading by example, using public transportation, riding bikes, walking, using more energy efficient devices and appliances. And if we do that more, just like if more and more of us let our lawns go, more people will think it's okay, more people will be willing to do it. So lead by example and use less energy.
Great. Thank you all. You have one more question?
I've got one idea. I know everybody probably does this. It's common sense, but always try to consolidate your trips. Plan ahead. When you go out in your car, do all your errands that time when you go. Plan ahead. Don't just think of your car as like, well, I'm just going to go now to get that one thing. Consolidate.
Yeah, great. Well, I think we've wrapped up at 8:30, which is pretty good. I want to be respectful of everyone's time. I want to go ahead, first of all, and give a warm round of applause to our panelists. Excellent job, guys. Thank you so much. I want to thank Naked City Brewery for hosting us again. I get tip your server. Thank you very much. And of course, Cascadia Climate Action. Other ways to get involved, please. There are some cards circulating around. If you enjoyed this event, if you want to see more events like this, fill out the card and make sure that it gets back to one of the volunteers here. We also have some cards circulating, ways to learn and get involved on climate change. A couple of things coming up that you might want to be aware of. If you enjoyed this event, we're going to be hosting another one November 2nd, the same venue, 7 p.m. It's Climate Science on Tap, Geoengineering and Climate Change. Going to be a really interesting panel, not only on the science of geoengineering, but also on the ethical and political issues associated with it. On November 1st, Climate Change and Nuclear Power in the 21st Century. That's going to be at UW-Thompson Hall at 6:30 p.m. So more information about that, you can get that on Cascadia Climate Action's website, as well as the calendar of events. Thank you, everybody.